The future can affect the past. That's right. Your adult decisions right now are affecting your childhood past. Well, on a microscopic level. John Archibald Wheeler is famously known for his bizarre and out-of-the-box theories, from the binary information theory to the one-electron theory. Not to mention that he also was the man who planted the seeds of curiosity inside the mind of his famous student scientist, Richard Feynman. You can say John Wheeler is basically George Lucas of quantum mechanics. But his ideas weren't just fun fictional theories to think about when you're bored. And they were actually a breakthrough in quantum world. For example, this respectful scientist theorized that the future can affect the past. This strange effect is called retrocausality. The strangest part is that scientists experimented it 30 years ago, and apparently he was right. Technically. Why is nobody talking about this? And how could a future event affect something that already happened? Well, we'll talk about it now. We are three-dimensional creatures living in a four-dimensional universe. The space that we move in is divided into X, Y, and Z, length, width, and height. I, as a human, can move freely in the space to up and down, left and right, forward and backward. Of course, Albert Einstein was the first person to suggest that the universe is not limited to three dimensions of space and an extra dimension of time exists as the fourth one and the 45-degree angle of all dimensions axis. As much as we're free when moving in the three dimensions of space, our movements in the dimension of time is limited to only forward. We might have some theories about how to move even more forward, like high velocity in the space or black holes event horizon, but it is still scientifically unproven that whether the laws of physics will bend and help us travel to the past. We can't technically say we are four-dimensional creatures, but the fourth dimension of time is more like a train and we are its passengers. A passenger can control the destination and he's only riding on the train. Still, relativity confirms that the value of time is equal to the other three space dimensions. While many thought that space and time are two different things affecting each other, Einstein hypothesized that space and time are actually a united entity. According to his block universe theory, not only considering time and space as two different properties is wrong, but he also believed that the past, present, and the future are happening in the same moment simultaneously. It doesn't really mean that time is like a stretching spaghetti, that every part of it is a specific moment in our lives that is happening at the same time. It just means that according to his block universe theory, it is not physically logical to define a specific event or a cause as happened, happening, or will happen. In our usual, ordinary, everyday life, we believe in the past as a gone moment, the present as an already happening, and the future as an arriving moment. But relativity says otherwise by introducing us with the relativity of simultaneity. According to this principle, every observer has a different perspective about the present moment. A still man and a man on a moving train and a man on a spaceship experience different time dilations depending on their velocity and their gravitational field. The word now depends on your motion in space throughout the cosmos. If there is no universal present moment, then the universe definitely doesn't have a massive clock or a timeline that is updating cosmically. Instead, physics describes reality as a fourth-dimensional space-time structure. In this giant 4D map, every event that has happened, happening, or will happen, all are points in this space-time. They all exist as a part of this structure. But still, when applied to the actual world, we humans are only moving forward in time. Why? Because of the second law of thermodynamics, which states that the entropy of the universe should always increase through time. All details were explained in our previous videos. This concept of time moving forward creates the logic of causality among us. Causality is simple. Every effect in the world comes from a cause. Every event we experience appears to follow this rule. A stone is thrown, then a window breaks. a star explodes, and only years later does its light reach Earth. This sequence seems so fundamental and daily for us that we rarely question it. In fact, much of science is built on the assumption that the past influences the future, never the other way around. Yet when physicists began exploring the quantum world, they encountered phenomena that seems to blur this distinction. Some experiments suggested that the way we choose to observe a particle in the present may affect how we describe its behavior in the past. This is where retrocausality starts. Before we move forward and explain the experiment, we must mention a necessary helpful hint that will help you understand the retrocausality experiment even more. And the problem is the observer problem, aka the bridge. We define the flow of time by the decay of order, but in the quantum world, the rules when and where start to dissolve. The core issue is that in quantum mechanics, nothing is real until it is measured. The catch is, how can we make sure the reality hasn't changed after we started measuring it? Now, let's not waste any more of your time and start actually talking about the experiment. As we explained a minute ago, through the experiment, scientists questioned the law of causality and doubted the idea that literally every cause in the universe should come before the observable effect. To explore this mystery, physicists proposed a thought experiment known as the delayed choice experiment. The idea builds on a famous double-slit experiment, where particles of light, called photons, can behave either like waves or like particles depending on how they are measured. As we hinted before, this is the observer problem. Normally this is already strange enough, but Wheeler asked an even more unsettling question. What if the decision of how to measure a photon is made only after the photon has already begun its journey? Imagine a photon traveling through an experimental setup. At first, it seems as though it must decide whether to travel as a wave, exploring multiple paths at once, or as a particle taking a single path. But in Wheeler's experiment, scientists wait until the photon is already on its way before choosing how to observe it. Surprisingly, the results suggest that the photon behaves in a way that matches the measurement chosen at the last moment. It is almost as if the photon never committed to be a wave or a particle until the measurement is made. To understand Wheeler's delayed choice experiment, imagine a single photon entering a device called a beam splitter. A beam splitter is a special piece of glass that transmits part of the light and reflects the rest. In quantum mechanics, a single photon encountering a beam splitter can enter a superposition, behaving as though it travels along both possible paths simultaneously. After passing through the first beam splitter, the photon has two possible routes. Mirrors are placed along these routes to redirect the path towards a second location, where another beam splitter may or may not be inserted. This second beam splitter is the key to the entire experiment. If the second beam splitter is present, the two paths recombine. The wave-like components of the photon can interfere with each other, producing an interference pattern. The detectors at the end of the setup then reveal behavior consistent with the photon having traveled both paths as a wave. If the second beam splitter is removed, the paths never recombine. The detectors can then reveal which route the photon took, producing results consistent with the particle-like behavior. In this case, no interference pattern appears. The surprising part comes from the timing. The decision to insert or remove the second beam splitter is made only after the photon has already passed through the first beam splitter and is well on its way through the apparatus. Classically, we would expect the photon to have already decided whether it was traveling as a wave or as a particle. Yet the result always matched the measurement setup chosen at the last moment. This creates an apparent paradox. If the second beam splitter is inserted at the last instant, the photon behaves as though it traveled both paths. If it is removed, the photon behaves as though it traveled only one path. It almost seems as if photons' earlier behavior depends on a choice made later. Wheeler summarized the mystery with a provocative idea. We may be wrong to imagine that a quantum particle has a definite history before measurement. Rather than changing the past, the experiment suggests that questions such as which path did the photon really take may not have a meaningful answer until the measurement itself is performed. Modern versions of the experiment have been performed using fast electronic switches, lasers, beam splitters, mirrors, and highly sensitive photon detectors. In some implementation, the measurement choice is made by a random number generator while the photon is already in flight, ensuring that the experimental configuration is not determined in advance. The results consistently agree with the prediction of quantum mechanics and continue to challenge our intuitive understanding of causality and the nature of reality. At first glance, this appears to imply retrocausality, the idea that a present action can influence a past event. However, most physicists do not believe the experiment literally changes the past. Instead, it reveals that our everyday picture of particles having definite histories may be incomplete. The experiment challenges the assumption that quantum objects possess well-defined properties before they are measured. Whether the results point to retrocausality, multiple realities, or a deeper theory that we don't yet understand remains a subject of debate. What is certain that Wheeler's experiment forces us to rethink one of our most basic assumptions, that the past is always fixed and independent of what we choose to do in the present. Wheeler's delayed choice experiment doesn't prove that the future can change the past, but it does challenge some of our deepest assumptions about reality. More than a century after the birth of quantum mechanics, physicists still debate what these experiments truly mean. Are we witnessing a limitation of our understanding or a glimpse into a deeper layer of reality? Whatever the answer may be, one thing is clear: the universe is far stranger than our everyday experience suggests. Could retrocausality effect be used in our daily life like medicine? Is quantum entanglement connected to these mysteries? Well, we'll leave this topic for another video. Until that day, do not stop wondering and be curious.